Look around you. Do you see a sidewalk, a road, or maybe a tall building? Chances are, you're looking at something made with cement. This simple gray powder is one of the most important materials in our world. It's the magic ingredient that holds our modern civilization together. Without cement, we wouldn't have the strong skyscrapers that touch the clouds. We wouldn't have the long bridges that cross wide rivers. We wouldn't even have the sturdy foundations that keep our homes safe and secure. Cement is the quiet, unsung hero of construction, a material so common we often forget it's even there. So, what exactly is this incredible substance? Cement is a binder. Think of it like a very strong glue for rocks and sand. When you mix cement with water, a chemical reaction starts. This reaction is called hydration. It causes the cement to harden and become incredibly strong. It doesn't just dry out like mud, it chemically changes into a new, rock-like material. This new material can bind together sand and gravel to create a super strong composite we call concrete. It's this ability to create solid, durable masses from loose materials that makes cement so special and so useful for building almost anything you can imagine. Before the invention of modern cement, building was a very different process. People had to rely on what they could find in nature. Early builders used simple materials like mud and clay to hold stones or sun-dried bricks together. These materials worked, but they weren't very strong or durable. Heavy rains could wash away a mud brick wall over time. For bigger and more permanent structures, builders had to cut and fit massive stones together perfectly. This took an incredible amount of time and skill. Imagine trying to build a giant pyramid or a grand temple by just stacking stones with nothing strong to hold them in place. The quest for a better binder, a stronger glue, is a story that stretches back thousands of years. Ancient civilizations were constantly experimenting. They discovered that certain materials, when heated, could be turned into a powder that would harden with water. The ancient Egyptians used a form of plaster made from burnt gypsum to help build their monumental pyramids. Later, the Greeks found that mixing lime with sand and water created a useful mortar. These early discoveries were important steps. They showed that it was possible to create artificial stone, paving the way for bigger, stronger, and more lasting structures that would change the world forever. Long before the first bag of modern cement was ever produced, ancient builders were masters of ingenuity. They used a variety of natural materials to bind their constructions together. The most basic of these was simple mud, often mixed with straw for added strength. This mud and straw mixture was used to plaster walls made of woven branches or to stick together sun-dried clay bricks. While effective for simple homes in dry climates, these materials were vulnerable to water and weather. A heavy downpour could weaken a wall, and structures required constant maintenance to prevent them from crumbling back into the earth from which they came. The ancient Egyptians took a significant step forward. Around 4,500 years ago, they discovered the properties of gypsum. They found that if they heated this soft mineral, it would turn into a fine powder. When mixed with water, this powder would recrystallize and harden, creating a durable plaster. They used this gypsum mortar between the massive stone blocks of their pyramids. While not as strong as modern cement, it helped to level the stones and hold them in place. This innovation allowed for the precision and scale of construction that still amazes us today, a testament to their early mastery of chemical engineering. Elsewhere, other civilizations were making their own discoveries. In ancient Mesopotamia and along the Indus Valley, builders used bitumen, a natural sticky black tar that seeped from the ground. They used it as a waterproof mortar for their brickwork and as a sealant for their water systems. Meanwhile, the ancient Greeks improved upon an even older technology lime mortar. They would burn limestone in kilns to produce quicklime. When mixed with water and sand, this lime mortar would slowly harden by reacting with carbon dioxide in the air. This created a much stronger and more water-resistant binder than simple mud or clay. The Romans would later perfect this lime-based technology, but the early versions used by the Greeks and others were revolutionary. For the first time, builders could create structures that were not just stacked, but were truly bonded together. This allowed for the construction of more complex forms such as arches and vaults, which could span greater distances. These early binders were the crucial stepping stones on the long road to creating a material that could be poured like liquid and harden like rock, a dream that would eventually be realized with the invention of modern cement. The ancient Romans were the undisputed masters of cement in the ancient world. They took the Greek idea of lime mortar and improved it dramatically. Their secret ingredient was a special volcanic ash called pozzolana, which they found in abundance near Mount Vesuvius. They discovered that mixing this ash with their lime, water, and broken stones created an extraordinary material. This Roman concrete was incredibly strong and remarkably, it could even harden underwater. This unique property allowed them to build structures that were previously impossible, like massive aqueducts, sturdy bridges and harbor walls that have survived for 2 millennia. The Pantheon in Rome, with its magnificent unreinforced concrete dome, stands as the greatest testament to Roman engineering. Completed around 128 AD, its dome is still the largest of its kind in the world. The genius of the Romans was in how they varied the concrete mixture. They used heavy basalt aggregate for the strong foundations and lighter materials like tufa and porous pumice stone near the top of the dome to reduce its weight. After the fall of the Roman Empire, however, this incredible recipe for pozzolanic concrete was largely lost to the world for over 1,000 years, a forgotten secret of a bygone era. For centuries, building technology reverted to using less durable lime mortars. It wasn't until the 18th century that engineers began to systematically study and experiment with cements once again. A British engineer named John Smeaton was commissioned to rebuild the Eddystone Lighthouse in the 1750s. He needed a mortar that could harden quickly and withstand the constant assault of the sea. Through careful testing, he rediscovered that a limestone containing a high proportion of clay produced a superior hydraulic lime, a lime that would harden underwater just like the Roman version. His work laid the scientific foundation for the next great leap forward. That leap came in 1824 from an English bricklayer named Joseph Aston. He developed a new method by heating a finely ground mixture of limestone and clay in his kitchen stove until the carbon dioxide was driven off. He then ground the resulting clinker into a fine powder. He called his invention Portland cement because the concrete made from it resembled Portland stone, a widely used and highly prized building stone from the Isle of Portland. This was the birth of the modern cement we know today, a material that was consistent, reliable, and could be mass-produced, forever changing the face of construction. Making modern Portland cement is a bit like baking a cake, but on a massive industrial scale with incredibly high temperatures. The process begins with quarrying the primary raw materials from the earth. The most important ingredient is limestone, which provides the necessary calcium. This is combined with other materials that provide silicon, aluminum, and iron. These usually come from sources like clay, shale, sand, or iron ore. These raw materials are carefully chosen and blended in precise proportions to ensure the final product has the exact chemical composition needed for high-quality cement. Once the raw materials are gathered, they are crushed into smaller and smaller pieces. This crushing and grinding process is extremely important. The goal is to create a very fine, uniform powder known as raw meal. Think of it like sifting flour before you bake. A finer powder will react more completely and evenly in the next stage. This grinding can be done through a dry process or a wet process where water is added to create a slurry. Either way, the result is a homogeneous mixture that is ready for the intense heat of the kiln. The heart of a cement plant is the rotary kiln, a huge, slowly rotating steel cylinder that can be over 150 meters long. The raw meal is fed into the upper end of the slightly inclined kiln. As the kiln turns, the material slowly tumbles down towards the lower end where a powerful flame heats the inside to scorching temperatures of up to 1,450 degrees Celsius, or 2,640 degrees Fahrenheit. This intense heat causes a series of chemical reactions, transforming the raw meal into new mineral compounds. The material melts and reforms into hard, rounded nodules about the size of marbles. This new substance is called clinker. After exiting the kiln, the red-hot clinker is rapidly cooled to preserve its reactive properties. The final step in the process is to grind this hard clinker into an extremely fine gray powder. A small amount of gypsum is added during this final, grinding stage. The gypsum is crucial because it helps to control the setting time of the cement when it is later mixed with water, preventing it from hardening too quickly. The resulting powder is the finished product, Portland cement. It is then stored in large silos, ready to be bagged and shipped to construction sites all over the world. Cement is the cornerstone of the modern built environment. Its importance in our daily lives simply cannot be overstated. From the moment you wake up, you are surrounded by it. The foundations of your house, the sidewalks you walk on, the pipes that bring you clean water, and the roads that carry you to school or work are all likely made with cement. It is the key ingredient in concrete, mortar, and grout, the materials that form the skeleton and skin of our cities. Without cement, we could not build the large-scale infrastructure projects that support our global population, such as dams, airports, tunnels, and sewer systems. One of the main reasons for cement's widespread use is its incredible list of benefits. Concrete, made with cement, is exceptionally strong in compression, meaning it can support immense weight, making it perfect for the columns of a skyscraper or the foundation of a bridge. It is also highly durable, able to withstand the forces of nature, from harsh weather to the constant wear and tear of traffic, for decades or even centuries. Furthermore, cement is resistant to fire and water, providing a level of safety and longevity that few other building materials can match. It is a material that provides permanence. Beyond its physical properties, cement is also incredibly versatile and affordable. As a fluid mixture, concrete can be poured into molds to create almost any shape imaginable, from simple rectangular blocks to complex curved architectural forms. This gives architects and engineers enormous creative freedom. A fun fact is that the global production of cement is so vast that it equates to over 1/2 ton for every single person on Earth each year. This massive scale of production helps to keep its cost relatively low, making it an accessible building material for everything from a garden path to a massive hydroelectric dam. The economic impact of the cement industry is immense. Cement is a fundamental driver of development and economic growth. The construction of new buildings, roads, and infrastructure creates millions of jobs, not just in construction itself, but also in the manufacturing, transportation, and engineering sectors that support it. For developing nations, the ability to produce or acquire cement is crucial for building the schools, hospitals, and transportation networks needed to improve living standards. In this way, that simple bag of gray powder is a powerful tool for progress and prosperity around the globe. Despite all its incredible benefits, the production of modern cement comes with a significant environmental cost. The cement industry is one of the largest single sources of carbon dioxide emissions in the world. These emissions come from two main sources. First, the chemical process of heating limestone, or calcium carbonate, to create clinker releases large amounts of carbon dioxide directly. Second, the massive amount of energy required to heat the kilns to 1,450 degrees Celsius is typically generated by burning fossil fuels, which also releases carbon dioxide. This presents a major challenge for a world trying to combat climate change. In response to this challenge, scientists and engineers are working hard to develop a new generation of green cements. One promising approach involves creating blended cements. In this method, a portion of the energy-intensive clinker is replaced with other materials that have cement-like properties. These materials, known as supplementary cementitious materials, often include industrial byproducts like fly ash from coal power plants or slag from steel manufacturing. Using these waste materials not only reduces the amount of clinker needed, but also helps to solve another industrial disposal problem, making it a win-win for the environment. Another exciting area of research focuses on fundamentally changing the chemistry of cement itself. Scientists are exploring new types of cement that require lower kiln temperatures or are made from different raw materials that do not release carbon dioxide during processing. Some researchers are even developing cements that can actively absorb carbon dioxide from the atmosphere as they harden, a process known as carbon sequestration. An interesting historical fact is that ancient Roman concrete has proven more durable than many modern formulations, prompting scientists to study its unique chemistry for clues to making better, longer-lasting, and greener cement today. The future of cement will be defined by innovation and sustainability. The goal is to continue harnessing the strength and versatility of this amazing material while dramatically reducing its environmental footprint. Through new technologies, smarter manufacturing processes, and the use of recycled materials, the industry is slowly transforming. As we continue to build and shape our world, the evolution of cement will remain critical. It is the material foundation upon which our civilization stands, and ensuring its future is sustainable is essential for the progress of humanity for generations to come. Another interesting fact: some modern concrete can even heal its own cracks using embedded bacteria that produce limestone.